It's so hot. I don't know why I live in this state. Hello, welcome back. Atmosphere of the early Precambrian. Let's talk about it. What the atmosphere looks and is made up of now is not what it looked or was made up of back in the day, 4 billion years ago. So let's explore that a little bit. Just touch on the atmosphere and the hydrosphere, quite different than they are now, back then. Both of these also played an important role in the development of the biosphere, and we'll get to that in the next section as well. So today's atmosphere is actually mostly nitrogen, right? We breathe air, and from that air, we extract oxygen, right? But that's only about 21% of the total volume of gas in our atmosphere. Now, nitrogen, by far, the biggest percentage. Very small percentage of all these other things. Quick note on carbon dioxide, all right? So carbon dioxide, it's a greenhouse gas, naturally occurring. It's great. It's what's helped to warm our planet. So people are like, carbon dioxide, it's only a little part of our atmosphere. Yeah, exactly. So even if we add a little bit more carbon dioxide by burning fossil fuels and all of those things, even changing this number a little bit goes a long way in creating climate change. So, quick note on that. So in the early Hadean atmosphere, this was kind of Earth's very first atmosphere. It was probably composed of mostly of hydrogen and helium as the solar system was forming, because that's the most abundant gas in the universe. If that was the case, it would have quickly been lost into space because Earth's gravity is not sufficient enough to really retain those in high amounts. Also in the Hadean, this is before Earth differentiated, it had no magnetic field because it had no core. Remember back, the spinning core is what creates our magnetic field, or the magnetosphere. So without a magnetic field, the solar wind would have swept away any of those gases. So you can see there might have been, some hydrogen and helium early on, but that really didn't exist for too long, if any, before other gases kind of started to kind of take hold. So we'll come back to this chart often. All right. So what about the Archean atmosphere? So once Earth differentiated and a core was formed and a magnetosphere was present, an atmosphere could begin to accumulate. Now the hydrogen and helium is already gone, but due to volcanic outgassing, this continual process of volcanic eruptions, the gases that come out of them can now be held onto by the Earth and Earth's gravity because of this protective magnetosphere. In fact, most of what comes out of a volcano is gas. We think lava and stuff like that. Most of what comes out of a volcano is gas. So nowadays, water vapor is the most common volcanic gas, but now volcanoes also emit things like carbon dioxide, sulfur dioxide, carbon monoxide, etc., nitrogen, hydrogen compounds, a number of other things. So this is a cartoon image of what the magnetosphere does as far as blocking the solar wind, which, if we didn't have that, would strip away our atmosphere. If our core decided just to stop spinning and the magnetosphere went away, the solar wind would rip away our atmosphere, exposing us to intense solar radiation, and get cancer and die and yada yada. Thank you, core. So anyway, getting back to the Archean atmosphere. So the volcanic activity, heavy volcanic activity that was occurring during the Archean, probably emitted the same gases as it does now, and thus an atmosphere began to develop. But, with one exception, lacking free oxygen and lacking an ozone layer. It was very rich in carbon dioxide, common gas expelled in volcanoes. And gases reacting in this early atmosphere probably formed ammonia and methane. These are very big greenhouse gases, so there's an atmosphere that lacks oxygen, a lot of greenhouse gases, so the early atmosphere would have been also much warmer than it was today. And this early atmosphere persisted through most of the Archean as well. So you can see in the Archean, we get a big jump in carbon dioxide, which is very different from where we are nowadays. So we get this big jump in carbon dioxide, but again, we also have some ammonia and methane, as well as nitrogen and some water vapor as well. So in this oxygen-free atmosphere, that's kind of important, but we can tell why that's the case. So the atmosphere what is referred to as chemically reducing rather than oxidizing. A reducing atmosphere will remove oxygen, reduce oxygen from any surface metal mineral oxides. Oxidizing does the opposite effect. It adds oxygen to things. And the oxidizing is actually the process that creates rust. We're taking iron and adding oxygen to it to make iron oxide, which is a rust. So in any case, the atmosphere was chemically reducing. It actually acted to remove oxygen from things instead of adding to it. The reason we know this is because we find a lot of, for example, the mineral pyrite, iron sulfide. If the atmosphere had more oxygen and it was an oxidizing atmosphere, we would add oxygen to pyrite and create iron sulfate, I believe, which would not be pyrite. So the fact that we see a lot of pyrite in Archean age rocks means there probably wasn't a lot of oxygen in the atmosphere, because if it was, pyrite really wants to grab that oxygen and then oxidize and rust and turn into something else. Same thing with uranite. Uraninite. Yeah. You add oxygen to it and you get a different uranium oxide. And so the fact that we see this lower oxygen uranium-based mineral means there wasn't a lot of oxygen in the atmosphere, because it really, really likes to grab oxygen. But since we don't see that, we see in this other version, well, that tells us these exposed minerals were exposed to a reducing atmosphere, one that really lacks oxygen. All right. Oxidized iron becomes more increasingly common in the Proterozoic rocks. That's the next unit. We'll talk about that, and that's when free oxygen becomes more present. So again, we don't see an increase in oxygen until we get into the Proterozoic. So not a lot of oxygen through the Archean, if not any. So through Earth's history, there's been, depending on who or what you talk to, but at least 5 different atmospheres, starting from the Hadean through the Archean and some derivations through Proterozoic and into what we have now. So coming from in this area, so from about 4 billion to 2 billion years ago, so this kind of spans the Archean. A lot of water vapor, increase in nitrogen, a lot of carbon dioxide. You can see really no oxygen. So with the introduction of free oxygen, there's 2 processes that would eventually start to increase oxygen as we kind of end the Archean, as we start to get into the Proterozoic eon. Again, these processes began in the Archean, and that's what helped to build up oxygen in the Proterozoic. Number 1 is photochemical dissociation. Sounds fancy. I'll try to describe it as best I can, which involves ultraviolet radiation kind of coming into our upper atmosphere. The sun doesn't just give us visible light. It gives us a number of different types of radiation. Light is a type of radiant energy. So we have infrared is another type of radiation that the sun gives us. Ultraviolet is another one. So in any case, ultraviolet is a bit higher energy than visible light. That's why ultraviolet radiation gives you sunburn. It's higher energy. So that's why you put sunblock on, to block the you can't see UV radiation. You see visible light, but we can't see UV radiation. So even though it might be a cloudy day, it's always best to put some lotion on to block UV radiation, because it's higher energy. In any case, this UV radiation, as it kind of ripped through the upper atmosphere, it disrupts water molecules, kind of rips them apart, and water is H2O, 2 hydrogens and 1 oxygen. So it kind of rips it apart into hydrogen and oxygen, starting to free up some oxygen. So this could account for about 2% of present day oxygen. And then more important were the activities of organisms that practice photosynthesis, taking carbon dioxide and then through its processes expelling oxygen. So these two things, as we're kind of starting or ending the Archean and getting into the Proterozoic, increased free oxygen in the atmosphere. So here we have UV light. As it hits the water vapor, turns it into hydrogen and OH, which is a hydroxide. And then you also get the UV light interacting with the CO2, breaking apart into carbon monoxide and oxygen. You add these two things together, and that creates O2, oxygen gas, plus hydrogen. So it's the first source of atmospheric oxygen. So now that we have O2, it too can further be broken down by UV light into oxygen and oxygen. And then one of those free oxygens partners with oxygen gas to make O3, ozone, and then plus ozone plus UV light can be broken apart into a single oxygen atom and O2 gas. So it's this kind of weird cycle where more oxygen makes more ozone, which makes more oxygen, which makes more ozone. So as we got this process going, that's what helped to start it, to ramp it up, along with photosynthesis. You probably remember all of this from 9th or 10th grade biology, or at least a little bit. Photosynthesis is a metabolic process in which organisms like plants and other and like phytoplankton, other plant-based cellular organisms, take in carbon dioxide and then mix with water, and then they use the energy from the sun to create organic molecules, food like sugar, as well as oxygen as a waste product. So even with photochemical dissociation and photosynthesis, probably no more than 1% of the free oxygen level of today was present by the end of the Archean. So this process began, but it needed to ramp up a little bit. Once free oxygen was present, as I mentioned, an ozone layer formed, and that helped to block incoming ultraviolet radiation. So that kind of started to calm things down a little bit, but with more ozone and a little bit of UV radiation, you get more oxygen. It's kind of a weird cycle. Let me go to this. So this is photosynthesis. So when a plant takes in carbon dioxide from the atmosphere and uses the water that it has in its system, and then when energy is added to it, you always need energy for a reaction to occur. So sunlight, this is energy. When it hits the chlorophyll parts of the plant cells, that helps to take this carbon dioxide and water and turn it into glucose, which is a sugar, which is a carb, which is a food, and then the waste product of that is oxygen. So that's how plants give off oxygen. So now we have photochemical dissociation of water into creating oxygen for the atmosphere, which also creates ozone. We also have the sunlight responsible for aiding in photosynthesis, which is also adding oxygen to the atmosphere. And again, at the end of the Archean, it's really small amounts, but everything is starting to get going. All right, starting to get going. All right, let's go ahead and pause there. So we touched on the early atmosphere of Earth. When we come back, we'll touch a little bit more on the hydrosphere. See you back here in just a second.